Yesterday we were looking at these maps with the Nazca Plate, Andes Mountains, South American Plate, and the Mid-Atlantic Ridge, along with Africa over here. And the last question was asking if the Mid-Atlantic Ridge is spreading apart by about 2.5 inches per year, what was going on with this Atlantic Ocean before that? Was it there? Did it always exist? And what's going on with the edges of these two continents, Africa and South America? Were there any changes to these two continents as these things were being pulled apart? So that's where we left off yesterday. So we're going to pick up there today, and we're going to go to our first slide. And we talked as a class, just to start us off. So if it's moving 1 inch per year, does that mean the oceanic plate material has always existed? And the answer to that would be no, because in that ridge we have magma coming up in the center, making new rock. So it hasn't always existed there. And we weren't sure about the changes. We know that the two continents would be further away from each other, so that's a change. And we were thinking maybe the shape would change a little bit because of erosion. Kind of water hitting the rocks and the beach all the time might change its shape a little bit. So we were kind of thinking that. Then we were wondering, could Africa and South America have once been together? And a lot of people said yes. Some people weren't sure. So we went to the next question. And if they were closer together or even touching, what would other areas like the Atlantic Ocean look like? And so it's kind of like if we have if Africa and South America are touching, there can't be any ocean. And if there is an ocean, then Africa and South America can't be touching. So we kind of went back and forth what we thought was going on there. So we assumed that they were moving, and we wanted to see, like, if we could know how much they're moving, like how long ago would they have been touching. So we're going to try to use the rate of motion to calculate how long ago they might have touched. So we look at this paper here, and I'm just going to read the top part to you. So it says scientific data. Remember from lesson 8 that the plates are moving at an angle away from the Mid-Atlantic Ridge, so we can't just measure the distance from one continent to another. And so if we look here, the ridge is not like a straight line just going down. It was kind of jagged and kind of curving. So what they're saying is wherever we're going to measure, we got to kind of understand where that middle of that line is so we can measure the distance. If we track back the continents to where they could have possibly touched at the ridge, the continents would have moved roughly 7,000 kilometers, or 4,300 miles, apart from each other. So the distance from this line here all the way across is going to be 7,000 kilometers, or 4,300 miles. So that's what the measurement we're talking about there. Scientists also estimate that the two continents move 48 to 56 millimeters apart from each other each year. Okay, and that's roughly, so about 56 centimeters is probably maybe around, I'm looking at my ruler here, about that much. So here is a pen for comparison, so about half of a pen, and 48 would be a little less. So about half a pen up to about maybe getting close to 2/3 of a pen length, and that's per year. And that's total, that's from continent to continent. So from here to here, it's growing by about 2.5 inches. So we had people kind of guess how long that might have taken. So we had, I don't know, I think somebody said 10,000 years. So we said 10,000 years with 48 millimeters per year would turn out to be, I'm grabbing my calculator here. So 10,000 times 48 gives us 48, 0, and 3 more zeros. So that's 480,000 millimeters. We have to divide that by 1 million because there's 1 million millimeters in a kilometer, because up here they told us kilometers. We have to go back to that. So I'm going to divide that number by 1 million. that equals 0.48 kilometers. That's a half of a kilometer. And we need to move it 7,000. So we haven't even moved 1 kilometer in 10,000 years yet. So some other people said, let's try jumping it. And they're also giving two numbers here. So if we went with 48 millimeters per year or 56. There's a little difference, depending how much it goes up here. So let's go to, I don't know, say 1,000,000 years. So 1,000,000 years times 48 gives us, of course, 48 million, which would make sense. Divided by 1 million, because there's 1,000,000 millimeters in a kilometer, will take us down to 48 kilometers. And we're still way off. So 48 kilometers, we know it moved 7,000, so we're still way off. Now we could keep doing this, and that's just kind of a slow way of doing it. So I'm going to kind of show you mathematically what we're going to do. What we've been figuring out is time in years, multiply it by the distance, 48 millimeters, that it's moving per year, which is time, equals, we're trying to find out the distance. Okay. So what happens is we multiply the time by the distance per year, that gives us distance. But if we go back to the top, so this is how we sometimes look at science. We look at the formula and we look at what we know. We know how fast it's moving, 48 to 56. That's this guy right here. We know that. We're looking at the distance. We know it's 7,000 kilometers apart from each other. We know that. We just don't know how to do this. That's the one thing that's missing. So what we can do is take this number, divide it by this number. We're just going to bring this to the other side. So we're going to say time equals distance divided by the distance per year. And that will give us the time again. And we'll get our answer. So you may not understand that part. You don't have to. I'm just showing you what you're going to do here. So on this page, that's what we're doing. We know our distance. We're going to convert it to millimeters because we know millimeters. So we're going to do 7,000 times 1 million. That'll come up to 7 billion. That's million, so 3 more zeros. So 7 billion divided by, so we're taking our distance divided by how much it moves per year, and that'll give us time again. So like what we just said in the last little part of the screen there. So I'm just grabbing my calculator again. So we've got 7 billion divided by 48 gives us roughly, I'm dropping off some of the different numbers here, so it's roughly 145 million years. And if we do the other one, so we still have 7 billion, because it's just taking 7,000 times a million. So 7 billion divided by 56, so we're just going to add up the other number and see what we get. So 7 billion divided by 56, we get 125 million. So what this says, so it's a much faster way of doing it. We know two numbers, so we just calculated time. So that means for Africa and South America to have gotten away from each other as far as they did, it would take 125 to 145 million years to do that, as long as they kept moving at that rate of 48 millimeters per year or 56. Okay, so we kind of have an idea how long it would take. Now we go back. So here's another thing we did. We did it on the board. It was a much larger distance, but and I'm just going to do it smaller here with the paper we have. So I have Africa, and we have South America. And obviously these are not life-size. Just trying to grab South America. There we go. So we got South America and Africa. And we could move them back. So say we have a certain distance here. I'm going to grab some sort of object. So we'll have this little pin. So let's just say that's 2.5 centimeters. So last year, because they're spreading apart each year, so they're spreading apart, if we run that backwards, like if it was a movie, last year they were closer. The year before that, they were closer. So we keep going back. So say this was 2 centimeters. So last year, I'm going to put that right there. I'm going to move it over to this side of it where that is. So I moved that one back 2 centimeters, and I would move this one back 2 centimeters. And obviously that's not the scale or anything, but we're just kind of showing you. Now in the real world, if it had moved this much, nobody would notice. Even if you've moved this much, nobody would notice. On paper, it couldn't even tell if you moved the end. And we keep going back. So we keep going back in time until we think they may have touched. The fact that they could have touched doesn't mean that they did. So now we got to look for evidence of how we think we know they were actually together. So we go to this. So there are a couple things we might be able to find. Maybe some fossils on both Africa and South America that might be of the same things. Maybe we look for different types of rocks that are the same on both places. That would kind of show that maybe they had been in the same area. Maybe we look at the shape of the continents and we kind of see if they could have been the same thing. And we're going to look at that in the next lesson. But one last thing we want to take a look at is a garbage can. So we're not going to be looking at garbage cans, but this is a good way of showing you. So let's say we took 6 garbage cans and we put them around the school, and in 1 week. And so there's like one in 6th grade area, one in 7th grade, one in 8th grade, one by tech, one by music, and one someplace else, doesn't matter. And we throw garbage in. And let's assume that on the first day, we have, for lunch, we have burgers. Okay, so I'm going to switch over to the camera here again. So let's say we have burgers the first day. So that was, say, a Monday. And then on a Wednesday, I'm going to skip a case. We don't have to see the whole week. So Wednesday we had tacos, and on Friday we had spaghetti for lunch. So what that means is when we put in the garbage can, we know that burgers are going to end up on the bottom, because if this is an empty garbage can on Monday morning, when we put lunch in, burgers are going to go to the bottom. Then we're going to throw some other stuff on top, and then we'll throw Wednesday stuff in. Here's my tacos, and some more stuff, and then spaghetti up on top. Okay, so the older stuff is going to be at the bottom. If you're at home and you're throwing your clothes in your bedroom, for dirty laundry, your stuff you wore on Monday will be at the bottom of the pile, right? Because that's where it's going to be. The stuff you just took off now will be on top. So same idea. New stuff on top, older stuff on the bottom. Should be the same thing with rocks. Older rocks should be on the bottom, and then new rocks get put on top. Okay? So newest rocks up here, oldest rocks down here. And if we're going to be looking for rocks and fossils that are going to help us figure out if Africa and South America were together, we need to find rocks that are 125 million to 145 million years old. So we're not going to be looking for rocks on the top. We got to go down to get to that time period. And one thing we also have to understand is this is not going to happen everywhere. So if we had another garbage can in the school during the same week, we should find the burger stuff on the bottom, tacos in the middle, spaghetti on top. But see how I drew a squiggly line and like a zigzag line? Well, that was that garbage can. So maybe that was somebody had a birthday party during lunch, so that's some Christmas or some birthday wrapping. But this garbage can over here was over by music, so they only have this. It's, that's this one, but they didn't have the party. And then on Thursday, this one had the squiggle, it was the same type of garbage, but then they had this type of garbage. Now, we could start arguing that these are not from the same week because they're not identical. But scientists aren't going to say that. They're going to be like, they're from the same week. even though they're not identical. Because if I look at the general pattern, I understand that this big pattern of the B, T, and the S is the same. And there might be some small changes in between because of other things. Okay? So for example, if we had this garbage, the B, T, and the S, so I'm just repeating what's up here, and this garbage can over here, we know this is not from the same week. They had tacos this week, but the S and the W doesn't match up. It's not the same meal, so we don't have the same garbage. And the B and the C, whatever this would have been from, maybe grilled cheese or something, I don't know, that doesn't match up. So these two garbage cans can't be from the same week. These can be, even though they're not identical. There's enough similarity with some of the major stuff to point out that they're from the same week. And we're going to be looking at that idea tomorrow when we start looking at rock layers. Rock layers are not going to be identical, but they're going to be kind of like this, where they're similar enough that we know that they're the same rocks. So that's what we did in class today, and we'll see you tomorrow.